Okay, this is our second video in Module 1, tying up some loose ends on mass spectrometry. I brought back up the mass spectrum of the first compound we looked at. If you recall, this compound was determined to have an exact mass of 477.2638, but we had decided that that's the M plus H molecular ion, so it's the exact mass plus a hydrogen in positive mode. And this exact mass that's observed is in the analysis is compared to the calculated mass. So it's important to know how that calculated mass is arrived at, and it's through a table or sources of the most abundant common isotopes. So this goes back to Gen Chem. What's an isotope? I'm not going to go into that right now. As it turns out, you can just look these numbers up for common atoms that appear in organic molecules, as you see here. So hydrogen, carbon, oxygen, nitrogen. The sodium I put in there because we saw in the other example how sodium makes its way into mass spectra. Chlorine is something I'm going to talk about in a minute. Okay, so if you want to arrive at this 477.2641 number, you would add up the atoms of this molecule, doing the math on the oxygens, carbons, and hydrogens, which is all that's there, and adding up these numbers for all the carbons, hydrogens, so 30 carbons times the exact number 12, 36 hydrogens, not counting the extra one that appeared. So it'd be 36 times 1.007825, and so on. That's how you get to this calculated mass. Then, of course, they're comparing the observed accurate mass with the calculated, and you see that there's only a difference of 0.3 millidaltons, if you put it in millidaltons, difference between. So that's a very good low error number. I include the chlorines in here because chlorine, some atoms are interesting. Mass spectrometry, it's going to have different observations for the whole periodic table. Chlorine, though, is a common atom, so and it's common in synthesis. So there are two common isotopes of chlorine, and the percentages of these are 77.8% of chlorine 35 compared to 24.2% or so of chlorine 37. So you're going to get, with chlorine, unlike a lot of elements, you'll get straight line. You'll get a peak for the 35, and then a space where another peak might, and then a peak for the 37. So CL 35, CL 37, with that space in between them. So if chlorine is a part of this molecule, for example, we would see near the molecular ion somewhere, we would see basically two molecular ions. One, and in this sort of proportion, 75-25 close to. That's very distinctive for chlorine. You may not know chlorine's there, but if you see these peaks, you have a suggestion there that you might have chlorine. Bromine is another one that has two major isotopes, but those are more like 50-50. And iodine and fluorine are one major isotope, so we don't have to worry about that. But you have a whole periodic table of phenomena like this to be explored if you go into mass spectrometry. Finally, there's the nitrogen rule, which is, as rules go, is quite specific. You can see how it's worded here. Basically, this molecule that we're looking at above has no nitrogens and would fall under the second one here, where it says that it should have an even mass because it has no nitrogen atoms. And as you see, it does have an even mass of 476 when you remove the extra added hydrogen. Okay, so that's there's lots more you could go into with mass spectrometry. There's a whole science of how fragments are formed and whether those are predictable for compound classes and so forth, but stop at this point. So, completing some more chemistry review, I want to talk about nucleophiles and leaving groups. A nucleophile, generically shown here, and we see OH as the only possible leaving group, but we know this is a terrible leaving group. And the reason it's a terrible leaving group is because if this nucleophile comes in and forms a bond there and displaces the OH group as a leaving group, we would end up with OH minus as the leaving group that has left, which is not particularly stable unless it's already going into a solution full of strong basic OH minuses, like a sodium hydroxide solution. That's fine, but normally this is unstabilized in any way that you can look at it. So normally unstabilized, for want of a better word. It's essentially a point source where there's no way for that negative charge to be distributed or further stabilized. It's all resting on one atom, oxygen. All the negative charge on one atom. So when reactions like this don't work, we have to look for ways to make OH a better leaving group. One way is to acidify. If you acidify, you protonate the oxygen, your nucleophile now can come in and form the new bond, displace this bond, and pardon me, there's an error here where there's an extra hydrogen. Fix that. Okay. So that has a lone pair there. This will have left then as neutral water. So this is a great leaving group that has left. Okay. Another way is to transform the alcohol group like this, and this should hopefully look very familiar, through a reaction, a derivatization in the presence of base, which would remove that hydrogen, deprotonate in base. That creates essentially a nucleophile of the oxygen, which at that point would have 3 lone pairs, can react with this compound to give you this derivatized alcohol group, which we often abbreviate as a tosylate, OTS. So the TS, this whole thing right here, is the tosyl group, or TS, sometimes TOS. You'll see it like that. This is now a great leaving group. It's a great leaving group because how it looks when it has left. So what makes a great leaving group, a better leaving group? You have to analyze that based on what it looks like after it has left. Once this has left, you have a negative charge on that oxygen. So actually this whole thing is leaving up here, with the nucleophile coming in, right? So this is a better leaving group because it's resonance stabilized. And if you have to review resonance, I would suggest doing that soon. We use resonance arguments to explain a lot of things. Resonance is not reactions. It has arrows that show the distribution of electrons. For example, these electrons can be redistributed in this way, giving a resonance structure indicated by a double-headed arrow. Leading to this, which is simply another form where electrons are redistributed. And then you can have another resonance form of that. And the more resonance forms, which I can leave this for you, the more resonance forms, the more stable. In other words, what defines a better leaving group? Stabilization of the resulting I can't write anymore. And anion. Stabilization of the resulting anion. So the result, or the resulting, if it's not charged, like water is neutral, that's perfectly stable. This is resonance stabilized. There's also inductive effects can stabilize. And so the phenyl ring here probably has a positive contribution through inductive effects slightly as well for stabilizing that tosyl leaving group. Okay, a little bit longer on that than I intended originally. That's okay. From the point of view of the nucleophiles, so we talked about leaving groups a little bit. There's plenty more to talk about there. Essentially, you want a good leaving group as judged by its stability once it's left. Now, from the point of view of nucleophiles, a lot of this should ring bells from previous work. The simplest nucleophile, literally, is like the addition of a hydrogen. However, you can't have H- floating around in solution like this. So sources of hydride, this is a hydride, the simplest nucleophile, simply adding a hydrogen, would be lithium aluminum hydride or sodium borohydride that deliver the equivalent of an H- nucleophile. So these would be important to review if those don't look familiar, or if the concept of a hydride nucleophile doesn't look familiar. It's very common to see these get added, a hydride added to a carbonyl group, for example, as a nucleophile. We've seen plenty of examples of oxygen and nitrogen and other heteroatom nucleophiles. So clearly OH- is an oxygen nucleophile that can attack. This is a region of high electron density, likely attacking a substrate that has some point at which it has a low electron density, like the carbon of a carbonyl group. Amines are typical nitrogen nucleophiles. There's sulfur nucleophiles. A negatively charged chlorine could act as a nucleophile in a sequence. So I've seen lots of these. These are mostly, when you think about it, related to functional group conversions. So, or interconversions. If you are adding this to something, there's a leaving group leaving, you're introducing a heteroatom or a functional group, basically like an alcohol or an amine. So you could be just going from one functional group to another. There's oxidation and reduction going on, technically speaking, but these are not really building. They could be adding handles to build off of on a molecule, but the pinnacle of nucleophile chemistry is carbon nucleophiles, which I'm sure comes as no surprise. And We did lots of this in organic 2. Hopefully you did too. So to review, I would say, in this regard, Grignard reagents. Oops. Reagents. Organolithium reagents. The Wittig reaction. And so there's, I'm going to direct you to more review videos that are actually already posted. All of these create new carbon-carbon bonds. Via essentially nucleophilic chemistry. There's other ways to do carbon-carbon bonds, as we'll find out. So clearly, making new carbon-carbon bonds is critical for molecules that, for the most part, exist as large carbon skeleton frameworks. We have seen different kinds of sites of nucleophilic attack. So say you have some nucleophile. Again, I'll just use the generic Nu. In the simplest cases, we just saw that displacing a good leaving group. We saw cases where it can attack the carbonyl carbon, kicking electrons up here, and then maybe further chemistry along the line there. This is driven by inductive effects because the carbonyl group is polarized, delta minus, delta plus. Hopefully you recognize that nomenclature. It's pretty important. Epoxides also have delta minus, delta plus inductive effects. A nucleophile will likely preferentially attack one or the other carbon of an epoxide unless it's symmetric. Everything I'm saying should be very familiar. Nucleophiles can add to the carbon, one of the carbons of an epoxide. This is a little bit unique because in the end then you have a nucleophile attached to this carbon. Fix this. Sorry, my apologies. You would have, here's that carbon, nucleophile attached to it, and now this carbon with the oxygen on it here, negative. Initially, so this, and then you could proceed to do more chemistry here. But notice the key that I wanted to point out here was that the nucleophile adds to the carbon adjacent to the carbon that has the oxygen on it, as opposed to the previous example where the nucleophile has to add to the same carbon that has the oxygen on it. We also saw examples of nucleophiles and the way they react with esters, amides, carboxylic acids, and so forth. And perhaps you've seen that arrow pushing abbreviated all in one step, although you should know that this is stepwise, and review that if necessary. So, but this is another way that you actually add the nucleophile to the carbon bearing the oxygen. What we're going to see in this first unit of Organic 3 is a way to add directly to the adjacent carbon of a carbonyl group. And that is using this as not the substrate, but as the nucleophile itself. We're going to find a way to modify this such that its reactivity is dictated by this form of it, where this now becomes nucleophilic. But the importance is clear because this is a carbon. It's a nucleophilic carbon that can form bonds, can form new carbon-carbon bonds. And so that the first unit that we go into in depth is enolate chemistry. That will describe a lot of this. So like I said, there's lots more videos on the YouTube channel, Organic Chemistry. So, but if you look in the Chem 362, excuse me, 362, Organic 2, under playlists. So in there you'll find the Wittig reaction, Grignard reactions, organolithium reagents, epoxides, and so on to review. I want this first week to give you time to review as needed. Time will get a lot more precious later. I urge you strongly to review anything that doesn't sound familiar immediately and use this time for that, because later we're going to be charging through new material and it all builds upon itself. Our ultimate goal is to have basically an understanding that you have like a toolbox of organic reactions that can be applied to the synthesis of more and more complex molecules, whatever they are. And so, you know, I'm just sort of randomly drawing stuff here. But how would you make something like this using the reactions we know? Okay, so this video is one of my longer ones, but it's the last one of this first module.